Well, good morning, GopherCon. I hope everyone is having a great time. That is great to hear. I was asking someone for advice on how to start a talk, and they said a way to really build passion is to start a flame war. So I wanted to ask, how do you pronunciate this word? Is it JSON with an emphasis on the J, or is it Jason like the name? So let's settle this debate once and for all. I want everyone to contribute. So raise your name if you think it's option one, JSON with an emphasis on the J. All right, that's quite a number of you. Put your hands down. Raise your hand if you think it is Jason as the name. I am very, very happy and pleased to report that option one wins, which is the camp I am in. Option two, you are all wrong, but we can all continue to be friends after this is over. All this playful banter aside, this is our agenda for today. We'll briefly review what JSON is. Then we'll talk about what the problems with the v1 encoding JSON package are. Then we'll present a possible solution to fix those shortcomings in a hypothetical encoding JSON v2 package. And finally, we'll discuss how v1 and v2 would theoretically interoperate, as we absolutely do not want to break the world. Before continuing, I need to give credit where credit is due. Improving JSON in Go has been a multi-year effort involving many engineers across a variety of different companies. This has largely been a volunteer effort, with each contributor not necessarily being formally sponsored by their employer. The set of contributors extends beyond even the people seen on this slide. Currently, Daniel and I serve as the de facto maintainers of the existing JSON package in the standard library. Now, with regard to the future of JSON in Go, we have a prototype implementation that we believe will bring JSON in Go to the next decade and beyond. For that prototype, Daniel and Johan did most of the code review. Roger and Chris did most of the design review, and I oversaw the general effort. I do want to thank my employer, Tailscale, for generously allowing me to have a fraction of my engineering time spent on this effort. If you ever find yourself wrangling with port forwarding or SSH tunnels, or you just have some fancy HTTP service you really want to share with your friends, you really need to check out Tailscale. Tailscale makes networking really easy. But let's talk about JSON. JSON stands for JavaScript Object Notation. It's derived from the JavaScript grammar and is mostly a subset of the grammar used for representing data. Undeniably, JSON is the most popular data interchange format in the world for storing structured data on disk or sending it over the wire. In JSON, there are 4 primitive data types: null, booleans, strings, and numbers. There are also 2 structured data types: objects, which are unordered sets of name-value pairs, and arrays, which are ordered lists of value elements. With these 7 data types, JSON is sufficiently expressive to represent most common data structures in the world, yet it remains simple and easy to understand. And this is why JSON is so popular over other formats like XML or CSV. Now, if you look at the set of JSON data types, you can see how it correlates with common types in Go. For example, a JSON bool matches a Go bool. A JSON string matches a Go string. A JSON number matches a Go integer or float. A JSON object matches a Go struct or map. And a JSON array matches a Go array or slice. The key idea here is that there's a reasonable correlation between the JSON type system and the Go type system. And we can map Go data as JSON data and vice versa. In Go, the encoding JSON package implements functionality for serializing Go values to and from JSON data values. The core functionality of the JSON package are the marshal and unmarshal functions, which use Go reflection to introspect any arbitrary Go type to derive a JSON schema for that type. This can be somewhat abstract, so let's look at an example. Here, on the left, we start with JSON data. we have 4 fields representing a device on a network. We take the JSON data, pass it to JSON unmarshal, to deserialize the JSON data into a Go value that semantically represents the input JSON data. The Go type shown on the right is the schema for the JSON data on the left. And of course, you can go in reverse by starting with the Go value on the right side, pass it to JSON marshal, which serializes it as JSON data that semantically represents the input Go value. We've now gone full circle, converting JSON data into Go data and back. Looking at this example, it's easy to see how Go strings, integers, and bools correspond with JSON data. But how do you handle custom Go types without an obvious JSON representation? Here, on the right, we have the net IP adder type, which is a Go struct without any exported fields. Yet, it is somehow serialized as JSON string with an IP address. How does that work? Well, the JSON package looks for types that implement certain magic methods. There are 2 sets of interfaces that allow Go types to customize their JSON representation. The marshal text and unmarshal text methods allows a Go type to be serialized to and from a JSON string. The net IP adder type implements these methods, which is how it can serialize an IP address as a string. Similarly, a Go type can implement the marshal JSON and unmarshal JSON methods to serialize any arbitrary JSON value, whether it be a JSON bool, number, object, or array. Between the 2 sets of interfaces, it's more flexible to implement marshal text if your type only has a representation as a string. This permits textual representation in more formats than just JSON, such as XML. At this point, we've reviewed the essentials of JSON serialization in Go, and we'll now transition to talking about the flaws in the current encoding JSON package and how we could fix them. However, before that, I want to talk about the place that JSON has today in Go. The JSON package is over a decade old and has overall held up pretty well. The idea of marshalling and unmarshalling arbitrary Go types with some default representation in JSON, combined with the ability to customize the representation, has overall proven to be highly flexible. In the upcoming slides, I'll be addressing the flaws of the package, but the goal isn't to disparage or disrespect the existing body of work, but rather to stand on the shoulders of all the previous contributions and to look forward to a brighter future. Also, the fact that JSON is the 5th most popular Go package indicates that we should tread very carefully in order to provide a smooth transition from what exists today to what may exist in the future. Even if changes are made for good reasons, there'll be a lot of code that continues to rely on the current package, and that code must continue to work well now and into the future. We cannot break compatibility, as that is one of the hallmarks of the Go programming language. With that said, let's talk about the problems in V1. And there are 4 broad categories: missing functionality, API deficiencies, performance limitations, and behavioral flaws. Let's dive into each of these. The first category of problems is that there are many, many missing features. At present, there are 92 open issues that affect a large number of programmers, and I'm sure many of you feel that sentiment. Now, addressing these wouldn't strictly require a V2 JSON package, but we do want to make sure that added features operate orthogonally with each other and do not have any pathological edge cases when they are used together. The second category of problems are API deficiencies. And unfortunately, these cannot be fixed without making a breaking change. Foremost is the inability to specify options with marshal or unmarshal, and also the inability to plumb options down the call stack to custom marshal JSON and unmarshal JSON methods. Today, you can technically specify options, but you must do so on an encoder or decoder type, which then also forces you to operate on an I/O writer or reader. This is unfortunate because it's an unnecessary merging of different concerns. For example, you should be able to configure unmarshal to disallow unknown fields without caring whether it's reading from a byte slice or an I/O reader. The semantic behavior of unmarshal is an orthogonal concern to where unmarshal is getting its input from. There's also no easy way to unmarshal today from an I/O reader without creating an intermediate decoder. The common pattern of calling decode immediately on a newly created decoder is actually buggy, as it does not reject trailing junk after parsing the first JSON value. As a minor deficiency, the compact, indent, and HTML escape functions write to a concrete type like bytes buffer as opposed to an interface type like I/O writer, which limits its flexibility. A third category of problems is performance limitations inherent to the API. Setting aside the implementation details of JSON that cause it to be slow, there are API designs that intrinsically limit performance, such as the marshal JSON and unmarshal JSON methods. On this slide, you see the signature of these two methods. The first problem is that marshal JSON always allocates. And because this is called through an interface method, the compiler cannot prove through escape analysis that it never escapes and must allocate on the heap. This causes pressure on the GC, leading to wasted CPU later on. The second problem is that marshal JSON and unmarshal JSON forces a second parse through the JSON text. When marshalling, the semantics require that it verify that the returned buffer contains valid JSON and also that it reformats that value to match the specified indentation in the encoder. When unmarshalling, the semantics require that the entirety of a JSON value be provided to the method call. It can't be truncated, and it can't contain trailing data. This forces the JSON package to parse until the very end of that JSON value before it can call the unmarshal JSON method. This is wasteful because any implementation of unmarshal JSON is going to parse the JSON text again. Because of the double parsing effect, this can result in quadratic runtime if the implementation of marshal JSON and unmarshal JSON methods recursively call the JSON marshal and JSON unmarshal functions. As an example of quadratic behavior, consider this contrived example of deeply nested JSON arrays. And let's suppose that every nested level is being unmarshaled into a concrete Go type that implements an unmarshal JSON method that recursively calls the JSON unmarshal function, as you see in the diagram. At the top of the call stack, we provide the input to JSON unmarshal. And in order for JSON unmarshal to call the unmarshal JSON method, it must parse to the end of the input to identify the boundaries of the inner JSON array, after which it can call unmarshal JSON with that value. Since unmarshal JSON recursively calls JSON unmarshal, the process repeats. In order for JSON unmarshal to call unmarshal JSON, it must parse to the end of the input and identify the boundaries of the input or JSON array. And this process goes on and 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 on until we hit the terminating base case for recursion. This inverted triangle represents the call stack of recursion and the amount of JSON text processed each step along the way. Using some geometry, we can see that this triangle has a height of n nested arrays. And since each JSON array occupies at least 2 bytes for the start and end brackets, this triangle has a width of 2n. Using geometry, we can see that the area of this triangle is 2n, leading us to the quadratic runtime of O of n squared. Now, nested arrays seem like a silly example, but this actually exemplifies a real problem. Any sufficiently complex custom type usually calls JSON marshal or JSON unmarshal recursively. Here's a real example from the Kubernetes codebase where an unmarshaled JSON method recursively calls JSON unmarshal not once, not twice, not thrice, but 5 times. This is much worse performance than O of n squared. As a spoiler for later slides, we sped up this use case by switching to a purely streaming JSON unmarshaler that doesn't perform redundant parsing of JSON. And the gains could be even greater on larger inputs. O of n squared grows really fast. A fourth category of problems are behavioral problems. First off, marshal JSON and unmarshaled JSON methods are not consistently called by the JSON package, depending on whether the underlying Go value is addressable. This might seem esoteric if you're not familiar with how Go reflection works, but the key problem is that user-defined marshal JSON methods are not called when you expect them to be called. This is certainly a bug, but previous attempts to fix it were rolled back because it broke too much code that inherently depended on this buggy behavior. Next, we have unmarshaled behavior. Next is the unmarshaled behavior that does not reject invalid UTF-8. This is quite plainly a violation of the JSON standard as specified in RFC 8259. Furthermore, JSON unmarshaling allows for duplicate names in a JSON object. This is technically permitted by the specification because it is declared to be undefined behavior. However, the acceptance of JSON objects with duplicate names can be a major security vulnerability, and we'll see an example of that in just a moment. Lastly, JSON unmarshaling uses case-insensitive match to correlate JSON object names with Go struct names, Go struct field names, that is. This is a highly surprising default to most users, and also a security vulnerability in the same class of failures as duplicate names. So let's look at an example of a privilege escalation exploit using duplicate names. Suppose we have Gotham Bank here, and they have a service for you to withdraw money. The bank is implemented in terms of 2 microservices. The authenticator is only responsible for validating the credentials in a JSON request. It rejects the request if the credentials are bogus. Otherwise, it forwards the request along to the accountant. The accountant is responsible for withdrawing money from that particular user, assuming they have enough funds. It does not verify the credentials because it assumes that the authenticator is doing its job. So let's suppose we pass in this JSON request. The username is Joe Tsai, the password is show me the money, and I'm trying to withdraw $1 billion. The authenticator inspects the request. My credentials matches the database, and so my request is valid and forwarded on to the accountant. The accountant now processes the request. It looks up the user Joe Tsai, completely ignores the password, and sees that I want to withdraw $1 billion. However, since I'm broke, the accountant rejects my request and tells me to go away. Womp womp. Now, it's important to note that this is not a permissions denied error, since we got past the authenticator, but rather it's a bad request since I asked the accountant to do an impossible task. I'm trying to withdraw money that I do not have. Now, if only there were someone rich enough that I could withdraw money from. I know, let's replay this scenario, but this time I'm going to maliciously modify the JSON request to include the username twice and specify the name of Gotham City's wealthiest benefactor, Bruce Wayne. As before, the authenticator inspects the request. However, since duplicate names are undefined behavior, the JSON implementation just so happens to report the first username of Joe Tsai and my password. This, of course, checks out. And so the authenticator passes the request on to the accountant. As the accountant inspects the message, It uses a different JSON implementation that handles duplicate names differently. Instead of reporting the first username, it reports the second username. From the accountant's perspective, it's Bruce Wayne wanting to withdraw money. Since Bruce Wayne is loaded, the accountant happily withdraws the money, and I've successfully stolen $1 billion from Wayne Enterprises. And since I'm filthy rich, this would be a good time to resign, and maybe I'll end my talk here. Now, why did this exploit work? Fundamentally, the semantic meaning of this request is ambiguous because the treatment of duplicate names is undefined behavior. The authenticator and the accountant use different implementations of JSON that disagree about the meaning of this request, and the attacker exploited that disagreement. To fix this vulnerability, we need to make sure that JSON parsing of values is precise about their exact meaning. Therefore, JSON objects with duplicate names should be rejected by default in v2 to avoid this kind of pitfall. Doing so would have completely avoided this fiasco in the first place. Up to now, we've covered some of the problems with the v1 JSON package. It has missing functionality, API deficiencies, behavior or performance limitations, and behavioral flaws. Let's now talk about a hypothetical v2 package. What I'm about to present is not a formal proposal, but a draft design intended to kick off discussion within the wider Go community. Nothing is set in stone, and everything is subject to change. It's also possible that a v2 JSON package never sees the light of day. With that disclaimer, here's a high-level diagram of our envisioned v2 API. Purple blocks represent types, while blue blocks represent functions or methods. The direction of arrows represents the approximate flow of data. The diagram splits JSON serialization into two primary components. The JSON text package on the bottom implements syntactic functionality that's concerned with processing JSON based on the grammar alone. It's designed to have a shallow dependency tree and does not depend on Go reflection. It's suitable for situations such as TinyGo, where binary bloat is a significant concern. We use the terms encode and decode to describe syntactic functionality, which is why the encoder and decoder are the primary two types for reading and writing JSON as a stream of tokens and values. They maintain a state machine that's needed to validate the structure of JSON. In contrast, the JSON package implements semantic functionality that determines the meaning of JSON values as Go values and vice versa. We use the terms marshal and unmarshal to describe that semantic functionality. The JSON package is implemented in terms of the JSON text package. And in order for JSON to marshal and unmarshal arbitrary Go values, it must have a dependency on Go reflect. There are three variants of marshal and unmarshal functions to handle common input and output types. Let's take a deeper look at the JSON text package. The core functionality is provided in the encoder and decoder types. They expose methods to read and write JSON tokens and values, which are constructs from the JSON grammar. This allows you to process JSON text in a purely streaming way by peeling off each token or value one at a time. You are not required to buffer the entirety of the JSON input in memory. The constructors, new encoder and decoder, take in variadic options that allow you to configure the operation of encoding and decoding. There are two basic data types for representing arbitrary JSON: tokens and values. A token represents the smallest structural unit in JSON. For example, the start and end delimiter of objects and arrays. In Go, it's implemented as an opaque struct type with constructors to create a token and also methods to retrieve a value. In essence, it operates as a union type, but is specially designed to avoid any form of allocation. A value represents the entirety of a JSON value. Unlike a token, it can represent an entire JSON object or array. Its Go representation is a byte slice containing the raw textual representation of JSON. The options type is an interface type declared in a shared internal package. It has no public methods and only serves as a marker type. There are several options to configure behaviors, like whether to allow duplicate names, whether to allow invalid UTF-8, how JSON strings are to be escaped, and how white space in JSON is formatted. Let's turn our attention now to the v2 JSON package. The core functionality is provided with the marshal and unmarshal functions. There are 3 variants of the marshal and unmarshal functions to handle common input and output types. You have byte slices, I/O writers and readers, and JSON text encoders and decoders. Each variant behaves semantically the same way, except that it operates on a different input and output format. To configure the behavior of marshal and unmarshal, each function takes in a variadic list of options. Since the default JSON representation of Go types may not always suit your needs, in v2 we provide users the ability to customize JSON in at least 2 different ways. First, similar to what you can do in v1, the marshal JSON and unmarshal JSON methods allow the author of Go types to customize their JSON representation. We will continue to support the v1 methods, but we also declared new methods in v2. The v2 methods fix the performance problems mentioned earlier by operating directly on a JSON text encoder and decoder, which entirely avoids the double parsing problem that led to quadratic behavior in the first place. Second, there are situations where you want to customize the JSON representation of Go types that you do not own. These may be types declared in a different module, or situations where it is not convenient for you to declare JSON methods. The marshal func and unmarshal func are generic functions parameterized on an arbitrary type T. This allows you to provide a custom JSON representation of any type T. Together, these 2 approaches provides great flexibility for customizing JSON representation and puts power in the hands of both the author of Go types, but also the caller of JSON functionality on other users' defined Go types. Now, similar to the JSON text package, there is an options type. The options types here is identical to the options type in the JSON text package. And the reason for this is because options in JSON text have relevance in the JSON package as well. The options type has a plural name because it represents either a singular option or a set of options. The default options v2 option represents the set of all options that defines v2 behavior. This is designed so that you can compose it with other options to toggle on and off options and behaviors. And this will become very important later on for interoperability. Additionally, there are a number of options to configure behavior, such as whether marshal JSON serializes maps deterministically, whether to format nil maps and slices as a JSON null or not, whether to perform case-insensitive name matching, whether to reject unknown object members, and so forth. Let's switch over to the changed API in the existing v1 JSON package. The only new API is our added options. And the options type here is an alias that is identical to the options type in the v2 and JSON text package. For every single changed behavior from v1 to v2, there is an option that backs that behavior change. I won't go over this full list, as many of the options here are fairly esoteric, and some only exist to provide bug-for-bug compatibility in the V1 package. It can be quite cumbersome listing every single V1 option, and so we provide a default options V1 option that represents the full set of all options that defines V1 behavior. I mentioned earlier that it's imperative that we have a good story for how V1 and V2 interoperate. We want to avoid the situation where half the Go ecosystem is stuck on V1 and the other half is stuck on V2. And there's no way to bridge this divide. By composing default options with individual options, we provide the ability to now gradually bridge this divide. The range of behaviors between V1 and V2 can be thought as a gradient of points on a line. At the two opposite ends of the line are the default V1 behavior, which you get with V1 Marshall, and the default V2 behavior, which you get with V2 Marshall. For brevity and clarity, the V1 refers to the encoding JSON package that you could import today, while V2 refers to the hypothetical encoding JSON V2 package that you could import in the future. The first variant of JSON or V2 Marshall is a call that passes in default options V1. Since default options V1 represents a full set of V1 behavior, this is configuring V2 Marshall to operate entirely with V1 semantics. In fact, this is identical to V1 Marshall. And the implementation of V1 Marshall will actually just be calling V2 Marshall under the hood with default options V1. The entirety of the V1 package will actually be implemented in terms of V2 with the appropriate set of options specified. Next, we have the exact same call, but we added an option at the end to disallow duplicate names. It's important to note that latter options take precedence over prior options. Using default options V1 as a base, we alter it for a single behavior. This is using mostly V1 semantics, except that it uses a single V2 specific behavior. This is mostly V1 with a little bit of V2. In this example, we have a V2 Marshall call where we no longer pass in default options V1. This means we are operating under the V2 semantics. However, we pass in two options that specify V1's behaviors. And this is mostly V2 with a little bit of V1. Lastly, we have a V2 Marshall call here where we pass in default options V2 as the very last option. This example highlights how latter options take precedence over prior options. Since default options V2 represents a full set of V2 behavior, it will override any options specified in the ... Any options in the middle will have no effect because they are overwritten by that default options V2. And this, of course, is semantically identical to V2 Marshall. The composability of options allows us to gradually migrate from V1 to V2 according to the options that matter to your specific needs and at the pace that is appropriate for your specific situation. Here are some of the notable changes from V1 to V2. We make invalid UTF-8 rejected by default to comply with the standard. We reject duplicate names by default to avoid potential security flaws. JSON object names now use a case-sensitive match for Go field names. Nil slices and maps are marshaled as empty JSON arrays and objects instead of null. Now, this last behavior change may be controversial. It is very clear from the issue tracker that we need to provide the ability to configure how nil slices and maps are to be encoded. But it's not clear that which one should be the right default. And this is where we need the community to provide feedback. Now, as I mentioned before, all the change behaviors have an option that back it. So even if the option doesn't work for you, there is still the ability to opt into a different behavior that is best suited for your use case. The JSON package allows you to alter the JSON representation of individual Go struct fields using struct tags. In V2, we redefine some tag options and add others. Omit empty, which already exists in V1, is being redefined to omit a Go struct field that would have marshaled as JSON null or an empty JSON string, array, or object. This changes the definition to operate not on the Go type system, but rather on the JSON type system. And in many ways, omit empty in both V1 and V2 operate the same way for most types. Now we do provide support for a new ability to omit, and that's omit 0. Omit 0 omits a Go struct field that is a 0 Go value, which is well defined in the Go language specification, or a Go type that has an is0 method that reports true. This resolves the highly requested feature to omit an empty Go struct like time.time. Some cases of omit empty today might want to migrate to instead use omit 0. Now, omit 0 and omit empty are composable, where either you can specify both together and it takes the logical OR of these two options. And a new tag option is the inline. Inline is the JSON equivalent of Go struct embedding. It allows you to forward all of the JSON object members of an inlined value into the parent object. Of particular note, the inline field can be a map of string of any or a JSON text.value. And this allows you to preserve arbitrary unknown object members of any JSON object. This allows you to write a proxy, for example, that can handle arbitrary unknown JSON object members and continue to preserve that and pass that down to a different service. Lastly, we support a new format flag that allows you to customize the JSON representation of certain Go kinds. For example, you can specify how nil slices and maps are to be encoded with regards to their nil, whether it's null or the empty JSON value. Whether byte slices are to be encoded as base 64 or hexadecimal encoding, or what format timestamps should use. Is it going to be a JSON number with the Unix timestamp, or some other custom format? Or what the format of time duration should be, or whether floats should support non-finite values like nans and infinity. Custom time formats in particular resolve a major pain point in the community for JSON and Go, where APIs in the wild use a wide variety of different time formats than just RFC 3339. And so this allows you to no longer have to create your own custom time type just to support that specific representation. Let's talk about performance. Here's the performance of the V2 prototype compared to V1 for marshalling concrete Go types. This graph shows the execution time normalized relative to V1 in blue, which is why it is always 1. The red bar represents the performance of V2. Further to the left is faster, and further to the right is slower. And we've got several benchmarks shown here. On the Cynthia Fahir benchmark, V2 is 1.4x faster than V1, while on the Twitter status benchmark, V2 is 1.1x slower than V1. Generally speaking, V1 and V2 are parity in marshal performance, which is mostly limited by the speed of Go reflection. And it's important to note that these benchmarks do not exercise the quadratic behavior of recursive marshal JSON calls. For pathological cases, hitting that case, the performance of V2 can be orders of magnitude faster. And we have measured this performance gain in a number of real-world production services. Here's the performance of V1 and V2 for unmarshalling concrete Go types. On the slowest benchmark, which is Canada geometry, V2 is still 2.5x faster. On the fastest benchmark, which is sit and log, V2 is 8.4x faster than V1. Now, while the V2 prototype is much faster, it does not use unsafe at all. Reliability, correctness, and safety is one of the high priorities for the V2 implementation. It is absolutely critical that any untrusted JSON input cannot cause something like a remote code execution bug in your service. And so we were very happy to accomplish these results. Now, it accomplishes these performance gains by using a much faster parser implementation that makes use of compiler inlining and many other tricks that have come to light in recent years. So in summary, today we talked about the problems with the V1 JSON package, how to fix them in a possible V2 JSON package, and how to make V1 and V2 interoperate. So what's next? Well, nothing I presented here today is set in stone. You want to stay tuned in the upcoming weeks as we'll be starting off a GitHub discussion to work out with the broader community for how V2 would potentially land. We know that this is going to be a major change to one of the most used packages, and we want to make sure that we deliver this right. We want to make sure the interoperability story works out for each of your use cases, that you are not left in a situation where you're broken forever. In fact, we do not even want to ever break you. If the community is happy with the results, we will eventually move forward with a formal Go proposal. Now, to be clear, it will certainly take at least a few Go releases at minimum before we can see this in the Go standard library. In the meantime, you can check out the V2 prototype and start playing around with the API. The implementation is subject to breaking changes. Every change that is breaking has a commit message with the words, warning, breaking change. It is your responsibility, if you do end up using this package, to check the commit log while upgrading the package. While it is a prototype, we are relatively confident in the correctness of the implementation, as it's already used in production in Kubernetes and at tail scale. Lastly, if you got questions, comments, or thoughts about JSON, I would very much love to hear them. So please come find me at the Tailscale booth downstairs. And thank you for your time. Have a great rest of your day.